Imagine, you come home after a long day, enter the building, and the elevator is out of order again. And it's not just broken, it crashed because of some stupid software bug. Again and again. Sounds familiar? Now imagine that one programmer didn't just curse and walk up to the 21st floor. He opened his laptop and started writing a new programming language. That's how Rust was born. And yes, it's not a joke, one of the most beloved languages of our time grew precisely out of that everyday frustration. Because of a broken elevator and dozens of flights of stairs climbed, one young developer came up with the idea for a personal project that eventually changed the entire industry. What began as a small side project on one developer's laptop has today become one of the most successful open-source programming languages used by Microsoft, Amazon, Google, Tesla, Discord, and many others. But how did a language originally written for himself manage to reach the same level as Java, Python, C, and C++? It's all about its unconventional approach to memory management. I'll explain it simply and clearly so you can understand exactly what makes Rust fundamentally different from other programming languages. And even if you've been writing Rust for a long time and consider yourself an experienced developer, don't rush to close the video. The story of this language can still surprise you. Well, get comfortable, and let's get started. Many software projects come into existence because a programmer somewhere had a personal problem that needed solving. That's more or less exactly what happened with Graydon Hoare in 2006. At the time, he was 29 years old and worked at Mozilla, the company developing the open-source browser we all know and love called Firefox. Coming home from work, Graydon discovered that the elevator in his building had broken down. He had to climb to the 21st floor, cursing everything under the sun, and then found out that the elevator had failed due to a software glitch. That's when he decided to try creating a programming language that would reduce such errors to zero so that even a beginner developer could write code that wouldn't hang or crash. Hoare understood the root cause of these problems very well. In many cases, such failures arise from memory management errors. The software for critically important systems, including elevators and other embedded devices, has traditionally been written in C and C++. These languages allow you to create very fast and compact code, but that efficiency comes at the cost of increased risk. They provide almost no protection for the developer against memory-related mistakes. Such errors can not only completely crash a program, but also lead to serious security vulnerabilities. According to Microsoft estimates, about 70% of critical issues in their software are related precisely to memory errors in C and C++ code. An ordinary person in Hoare's place would have just sworn and moved on, but he chose a different path. He opened his laptop and began designing a new programming language, one that would allow writing fast and compact code without the typical memory-related bugs. He named this language Rust after extremely resilient fungi that, as he put it, are over-engineered for survival. In general, there's a very important idea in this story. Big projects often start not from the ambition to change the world, but from a simple everyday problem and the desire to find a tool you can trust. In working on Rust, Hoare drew on ideas from languages that had appeared long before, such as LU, Erlang, and Limbo. He believed that many solutions from the past had been undeservedly forgotten, even though they were exactly what could address the challenges of modern programming. Hoare himself described Rust as technology borrowed from the past to protect the future from its own mistakes. And over time, other language developers embraced this idea as well. Almost 20 years have passed, and Rust has become one of the most popular languages in the world. About 2.5 million developers write in it, and corporations like Microsoft and Amazon consider it strategically important. Discord uses Rust to speed up its infrastructure, Dropbox uses it for file synchronization, and Cloudflare processes more than 20% of all internet traffic with its help. For nearly a decade now, Rust has topped the Stack Overflow survey as the most loved programming language among developers. What's more, even the United States government actively promotes the use of Rust, viewing it as a way to increase the security of critical systems. As often happens with open-source projects, Rust quickly stopped being the work of one person and turned into a collective effort. Today, hundreds of contributors from around the world work on the language, and a significant portion of them are volunteers. Graydon Hoare himself stepped away from active development back in 2013, calmly handing the project over to other engineers, including members of Mozilla's core team. In general, creating a programming language isn't all that rare. Many developers regularly experiment and make small languages as side projects. But only in exceptional cases do such experiments break out of a narrow circle and become truly massive. Even rarer does a language secure a spot in the major leagues alongside JavaScript, Python, or Java. So how did Rust manage to travel this path? What exactly made it so special? To understand this, you need to look under the hood and figure out how different programming languages handle a computer's memory. To simplify, dynamic memory can be thought of as a large whiteboard. While a program is running, it constantly places small chunks of data on this board, keeps track of where everything is, and erases what's no longer needed. However, the ways different languages manage this board vary greatly. Classic programming languages C and C++ were originally designed to give the programmer maximum control over how and when memory is used. This approach is genuinely useful. With full freedom, a developer can squeeze the maximum performance out of the hardware. That's exactly why C and C++ are still widely used for writing low-level code, the kind that interacts almost directly with hardware. All sorts of systems run on such code, from medical devices and cash registers to elevators and industrial equipment. The kernels of Windows, Linux, and Mac OS are still largely written in C. However, this approach has a downside. For high speed and control, you pay with complexity and risk. Languages like C and C++ demand extreme attentiveness from the programmer. You need to know exactly which memory is in use and when it should be freed. The slightest mistake can cause a crash. A program might try to access a region of memory it thinks is free, even though data is still there. And in the worst case, this can open a vulnerability for attackers. If an application doesn't clean up memory properly, sensitive data, passwords, financial information can remain in it and be exploited by malicious actors. As projects on C++ grow, even the most careful developer will eventually run into memory-related bugs. The larger the codebase, the higher the chance of accidentally introducing a memory leak, buffer overflow, or that almost impossible to track segmentation fault. Let's be honest, everyone who has worked with low-level languages has at least once caught a memory bug that was incredibly hard to reproduce and debug. It was against this backdrop that, in the 90s, a new wave of programming languages appeared: Java, JavaScript, Python. They offered a fundamentally different approach: relieve the developer of most responsibility for memory management. To achieve this, they introduced garbage collectors mechanisms that automatically clean up memory while the program is running. As a result, it became possible to write code without practically thinking about memory errors. However, this convenience came at a price. Automatic memory management took away the precise system control that C and C++ had always been famous for. Moreover, the garbage collector itself consumed resources. Applications used more memory and periodically experienced performance drops when the garbage collector took CPU time. Gradually, the world of programming split into two camps. If a program needed maximum speed or had to run on constrained hardware, embedded systems, the choice almost always fell on C or C++. If it was about web services or mobile apps, more and more developers switched to languages with automatic memory management. When creating Rust, Graydon Hoare tried to combine these two approaches. He wanted the programmer not to have to manually manage data placement. In memory, the language itself should handle that. But in exchange, Rust introduced strict rules about how data can be used and passed within the program. These rules are more complex than in Python or JavaScript, and they take time to master. But in the end, the code becomes memory safe, and the risk of introducing critical bugs is practically eliminated. And no less importantly, from the very beginning, Rust was aimed at solving another key problem of modern programming: concurrency. Modern applications perform many tasks in parallel, and different threads often try to access the same memory region almost simultaneously. In traditional languages, such situations easily lead to hard-to-catch and unstable bugs. In Rust, however, the memory model and type system are designed so that such conflicts are detected ahead of time and simply cannot reach the execution stage. When Hoare first opened his laptop to start working on Rust, he already had nearly a decade of professional experience behind him, and he was working full-time at Mozilla. The new language wasn't conceived as something massive. Initially, it was just a pet project. For several years, Hoare methodically worked on it alone, and when he started showing the results to other programmers, the response was mixed. Yes, there were enthusiasts, but much more often he encountered skepticism, eye-rolling, and phrases like, "This will never work," or "No one will ever be able to use this." Nevertheless, Mozilla's leadership became interested in the idea. It became clear that Rust could help create a more reliable and secure browser engine. Browsers are one of the most complex software systems, and memory management errors are especially dangerous in them. In 2009, Mozilla decided to officially support Rust. The language remained fully open and community-governed, but the company was ready to invest in its development by funding engineers. The Rust team occupied a separate meeting room in Mozilla's office. Mozilla Research co-founder Dave Herman ironically called it the Nerd Cave and even hung a sign on the door. Over the next 10 years, Mozilla hired more than a dozen full-time engineers who worked on Rust's development. According to project participants' recollections, interest in Rust quickly spread beyond Mozilla. Already in the early 2000s, volunteers from all over the world and from various corners of the industry began joining the development. Among them were engineers from large tech companies, as well as, for example, a schoolboy from Germany who became one of the project's notable contributors. Over time, Rust was officially presented at a professional conference and began rapidly gaining recognition. Its development accelerated, and the community grew. In the early 2000s, Mozilla engineers, along with community members, actively refined Rust's core and its memory management model. Although the ownership idea had been present in the language from the beginning, it was during this period that it was deeply reworked and brought to a practical form. The ownership model assigned exactly one owner to each piece of data at any given moment and introduced strict borrowing rules. This approach made it possible to catch most memory-related errors even before the program ran. The Rust compiler played a key role here. It strictly checked compliance with ownership and borrowing rules, and if the code violated them, the program simply wouldn't compile. As a result, entire classes of errors like use after free or data races were eliminated at the build stage. Many of the ideas underlying Rust had been known long before it, but the language's developers managed to turn those theoretical concepts into practical and convenient mechanisms for everyday development. According to Nico Matsakis, one of the key members of the Rust team, it took the developers a long time to figure out how Rust should actually work. The team constantly experimented with new language features, introduced them, tested them, and without regret abandoned anything that didn't feel right. As Steve Klabnik later aptly put it, Rust has dropped more features than many languages ever had in the first place. As this system developed, the need for a built-in garbage collector gradually disappeared. By 2013, it was completely removed. This is especially noteworthy considering that the very first versions of Rust used a garbage collector to ensure memory safety. Only over time was it replaced by the ownership and borrowing system, the very mechanism that today is considered the language's key feature. This allowed Rust programs to run faster and more predictably, without periodic pauses related to automatic memory cleanup. According to Hoare, some engineers might object that Rust still uses mechanisms that separately resemble garbage collectors. As an example, they usually point to reference counting, which is part of the memory ownership system. Nevertheless, Rust achieved impressive performance, approaching the level of C and C++ while maintaining strict memory safety. In May 2015, the first stable version of Rust was released, and the language began to be actively used in practice. Mozilla introduced Servo, an experimental browser engine fully written in Rust, and in 2020, Dropbox released a new version of its synchronization engine, the component responsible for exchanging files between users' computers and cloud storage. The key point was that this critically important part of the system was completely rewritten in Rust. Rust's evolution would have been impossible without the Cargo and Crates.io tools. Cargo simplified project building, dependency management, and testing, while Crates.io became the central hub for distributing community-created libraries. The rapid rise in Rust's popularity caused some concern among the project's early participants. On one hand, interest from corporations like Amazon and Microsoft dramatically increased the language's visibility and accelerated its development. On the other hand, questions arose about how the influence of large companies might affect the project's future. These corporations have the ability to hire full-time developers to work on Rust, which inevitably strengthens their role in decision-making. Today, several leaders of key Rust teams work at Amazon and Microsoft. Won't the interests of big players eventually start dictating the direction of its evolution? That's exactly why, in 2021, with the support of the largest tech companies, the non-profit Rust Foundation was created. Its mission became supporting independent developers and volunteers who contribute to the language's development. The foundation began providing grants, including amounts around $2,000, to those working on key Rust features, as well as running special assistance programs for developers who found themselves in temporarily difficult financial situations. In addition, the foundation took over funding Rust's server infrastructure and paid for the services of a company that ensured 24/7 operation of those servers. Previously, such tasks had fallen on the shoulders of ordinary volunteers. It sometimes reached the point where individual community members were effectively on permanent duty. What in the early years was perceived as an experimental project has over time become a solid, established technology. Rust, which appeared in 2006, is today at the stage of active adoption in industrial development. It is increasingly used in major industries, including the automotive and aerospace sectors, to create code responsible for high-performance systems. According to Dropbox representatives, Rust will be applied more and more widely over time. Microsoft executives have also publicly hinted at what many tech companies have long said informally. In new projects, Rust will be used more often, gradually reducing dependence on C and C++ where it makes sense. Today, these statements are already being confirmed in practice. In 2025, Linux kernel developers officially removed the experimental tag from Rust support. The lead developer of the Rust for Linux project, Miguel Ojeda, stated outright that the experiment had been deemed successful and that Rust would remain in the Linux kernel. It is already used in production environments, supported by major Linux distributions, and on millions of devices it is effectively present through the Android kernel. Although not all configurations and build tools are fully ready yet, Rust support is now considered a full-fledged part of the kernel, not a temporary experiment. That's all for today. A huge thank you to everyone for watching, and see you later.